So this problem is from the Basic Principles and Calculations in Chemical Engineering by Himmelblau and Riggs, the 8th edition. This is found in page 165 and 166. So we start first with material balance, no? How we do material balance in DWSIM. So we have this problem where we have a gas containing 80% methane and 20% helium, sent through a quartz diffusion tube to recover the helium, and we have 20% by weight of the original gas is recovered, and its composition is 50% helium. So calculate the composition of the waste gas if 100 kilogram moles of gas are processed per minute. So let's take note. I think we don't need to draw a diagram for the problem because this is pretty much close to a diagram, no? So where we have our input as this one, so let's call this the feed. I'm sorry. Uh, let's call this the feed. And of course, this is the waste gas and the recovered gas. So I'm sure, I think you know this, but when we're talking about gases, this 80% and 20% refers to the molar percent, right? While here we have a 20% by weight of the original gas is recovered. So meaning this is the weight of the meaning I'm sorry, 20% weight of the original gas is recovered. So the feed where we have the mm, where we have 100 kilomoles of feed, right? Where we have 100 kilogram moles. I'm sorry, moles per minute. Okay, so where we have 100 kilograms mole per minute of feed, we need to convert this into mass flow. I'm sorry about my handwriting. I think Google Jamboard responds slowly, so I could not really. Anyways, so we need to convert this to mass flow, and 20% of the feed mass flow goes to the recovered gas. And of course, since this is a steady state system, 80% of that mass flow goes to the waste gas. So 20% to the going to the recovered and 80% going to the waste. So now we are to determine what is the percent helium and percent methane in the waste gas. Okay, so this should be molar percent, right? And of course, if this is 50 molar percent of helium, then it's also 50% methane, right? So let's go ahead and use the DWSIM in solving this problem. So I have opened the app already, the software, and we'll just click create new. And okay, so let's click next, and we have methane. Take note, guys, if we solve or if we do simulation here in DWSIM, our chemicals or our compounds must be coming from the same database. Because when you try solving compounds from different databases, I think it will return an error as based on my experience. So since this methane is from the ChemSep database and the helium is like also from the ChemSep database, so we should have no problem with this. So this is just a mass balance problem, a material balance problem. So we are not really computing for the properties of our streams, right? Like the viscosity, the volume, or the flow properties. So it doesn't really matter what um, um, property package we use. So I think by default, let's use the ideal, the Rails law package. Okay. And for the system of units, I think it was mentioned kilogram moles per minute. Okay, so here the molar flow rate is moles per second, so that is gram moles per second, and we could not change that. So let's choose this one. Okay, so from the molar flow rate options, we can only choose either kilomoles per second, per hour, or per day. We don't have a per minute option here. So let's just click kilomoles per second, and I think we're good. So let's click on finish. Okay, so this problem is, we have a feed here and it is separated into two streams. So for in the DWSIM, our our first guess would be to use the stream splitter, no? But the difference between the stream splitter and the stream mixer is that for the splitter, like when I click the splitter, it will split, no, it could take one input and split it into three output streams, right? One inlet and three output streams. So what this does is it will just split the input stream into two or three streams using this calculation, no? Split ratio, mass flow specs, or mole flow specs. So I have actually um, tinkered a little bit on this software earlier before creating this video. So I found out that when we have an input stream, say this one, no? When we have an input stream and say we have two output streams, and if we choose material stream as our input and output stream material 2 and material 3, and say, let me just pause this, no? Let's pause this and say we have 100 kilogram 100 kilomole per second, for just an example, no? So if we do the split ratio, say 50-50, then and then click solve, then what this does is just to distribute 100 into two streams, 50 and 50 kilomoles for stream 2 and also 50 kilomoles for stream 3. It doesn't really um, play with this one, no? The whatever is the composition. So it will just divide the streams into diff it will what this splitter does is it will take the one input stream and we'll just divide it into two streams, diba? Two streams with different flow rates, but it will contain the same composition, no? So if we have a half and half methane and helium as our input, we would expect na material stream 2 would also have half and half na methane and helium, as well as material 3 half and half, no? So even if we play with this like that, for example, then we would get a 62 kilomole per second here, and 38 kilomole per second here, based on this split ratio, no? But we would still get the same compositions, no? Half 50-50, right? 50-50. So using the splitter would not solve this problem, because in this problem we have one input stream and it separates it. There is a mechanism here that concentrates the helium, no, in the recovered gas. Okay, so the purpose of this um, equipment here is to concentrate the recovered gas with helium, diba? So the splitter will not work for this problem, and I have also thought of using this one, but I could not find a I couldn't find an instruction manual or a video with this, no, and I'm getting errors, or I can't seem to figure out how to use this, so that's why I'm not gonna use that here in this video. So what we'll do here is to use this, the um, mixer, but we have to sort of invert our problem, no? Let's make our output streams as our input and our feed stream as our output. Okay, so this is so let me delete this first. So I just press the delete button and click on yes, and let's rename this one first, no? So let's call this the feed stream. Let's call this the, click on this and rename it as the recovered gas. Recovered. And let's rename this as the waste gas. And as I've mentioned, let's invert the streams, making this as our input and the feed as our output, to utilize the um, this one. So let's just call this a mixer, no? Okay. So now for the mixer, we choose the recovered gas as our inlet, waste gas as our inlet, and in our output stream is the feed. So in contrast with the splitter, the mixer actually considers the concentration of the incoming streams, no, and it will actually mix the two streams, no, and so it will be combined and produce a feed with, so this is a steady state system, right? So the feed will have, the total flow rate of the feed will be the sum of the flow rates of the input streams, and also its composition is based on what is the composition, or what is the compounds coming in to the mixer. So the amount and percentage of methane and helium going in here, and the amount and of this waste gas flow stream and the percentage of methane and helium going in here is all accounted in here. So we can use the stream mixer for this mass balance problem. Okay, so the feed, we know that the feed is 100 kilogram mole per minute, but um, our DWSIM units only allows us to choose the kilogram mole per minute. So converting 100 kilogram mole per minute into 100 kilogram mole per second, we just simply divide it with 60 seconds per minute, diba? So that would give us 1.667, diba? So let's just let me write this here. So 1.667 kilogram mole per second. And we need to convert that into um, weight, kilogram per second na flow rate. So I think we need to disconnect this first. Sorry. Um, we need to disconnect this first and set because we have to know the mass flow rate when the molar flow rate is what is that again? When the molar flow rate is 1.667 kilomoles per second, we need to know what is the mass flow rate for a stream with 80% methane and 20% helium. So let's click on compound amounts, and this should be zero point 0.8 and this should be zero point 0.2, right? So click accept changes, but this one should be 1.366. Let's just use 4, 6, and a 7. So it automatically converts the 1.667 kilomoles per second when we have 80% methane and 20% helium, accounting for their molar fraction, their molecular weight. Then their mass flow rate is 1363.45. So let's um, write that here, 1363.45. That is in kilogram per second. Okay, so since we know that 20% by weight of the original gas is recovered, so therefore the mass flow rate of the recovered gas is 20% of this, no? So let's compute for 20% of 1363.45, and that is 272.69 kilogram per second. So automatically the balance is 80% of this one is the waste gas. So let's just how do I, okay, 1363.45 times 0.8 is the waste gas. So that is N90.76. Okay, so 1090.76 kilograms per second. So let me connect this again into our mixer. So I will just pause the automatic computation of DWSIM, no? So outlet stream should be the feed. And okay, so now we know that the recovered gas, which contains 50% helium and 50% methane, okay, its stream conditions is that it is, oh, I'm sorry, it should be, sorry, wait, kilogram per minute, okay, um, I was wrong, so this should be kilogram per minute, no? Um, kilogram per minute, okay? This one also should be kilogram per minute. Okay, so going back, the recovered gas should be 272.69, 272, okay, let me just click this, 272.69 kilogram per minute, the recovered gas, and it should be, um, okay, so now I have to click on solve. Okay, go. So this is now 0.5, 0.5, and the stream conditions is that it is 272.69 kilogram per minute. Okay, and now for our waste gas, it is 1090.76. So 1090.76. And we still don't know this. This should be our unknown, right? So now what we do is, yes, we're sure that the mass flow rate is the sum of the mass flow rates of the two incoming, so the recovered and the waste. So it should be 1363.45, right? And this should be 80, but now it's not 80, it is 50-50 because our input is 50-50 and our input here is 50-50. So if I change this, for example, into 0.2 and 0.8, click on accept changes, keeping this the same, no? As you can see here, it changes, diba? So to solve this problem, we need to guess a value for this one so that we could reach a zero point 0.2 composition of methane and zero point 0.8 composition of helium because that is the given. So what we did is we just reversed the problem. So to make our um, guess, or this is like a trial and error solution, no? So to make this easier, let's create a property table. So just what I did is just click this one and this one popped up. So I have, it says double click to edit. So I'm gonna choose the feed and let's choose the mass flow, the molar flow of the feed, and we are interested with the um, mole fractions, right? The mole fraction of methane, molar fraction of methane, and the molar fraction of helium. So molar fraction of helium. I think that's it. And maybe we could determine if our, just to check now, just out of curiosity, let's check if what is the molar fraction um, uh, molar fraction of the liquid and molar fraction of the, where's the fraction of the vapor? Okay, molar fraction vapor and molar fraction liquid. So when you're done clicking on those properties, just click the close button and we have this. No, so what we know is our feed is pure vapor. No, it's a gas. And right now the composition is that it is 24% methane and 76% helium. So our mass flow is 1.363. So I think we need to get a lower na flow rate. Do we? I know. I think it's correct. Okay. So anyway, um, so what we're doing now is to guess um, the composition of methane and helium in the waste gas. That will give us 20% helium and 80% methane in the um, sorry, 80% methane, 20% helium. Okay, so in the feed stream, so let's say this is, I think this should be 0.88 and 0.12. Are we accept changes? Methane is 78 and helium is 22. Okay, so getting there. So let's increase this into maybe 90 and 10%. Oh, so we're almost there. I think this is it na. So maybe 0.11 and 0.89. Oh no, so it should be somewhere between that, no? 8, maybe 8, 9. Um, how about 90.05 and 1, it should be 0.95, am I right? Okay. Okay, so pretty close. So maybe 908 and 0.92. Yeah, I think this one is okay na. Or if you want it to be okay, I think this one's okay na. So our answer is this one, no? So now our molar flow rate is close to 100 kilomole per minute, right? Because it should be 1.667, di ba? And our mass flow rate is this when we convert molar to mass. And our molar fraction now is 0.7959 and zero point 0. So you could still play with these values, no? So if you really want to come up with a zero point 0.8 na methane and a zero point 0.2 na helium, 'di ba? Okay. So that's what we did here. So again, let me just let me just rewind, no, or summarize that what the splitter does is it will just divide the input stream into 2 or 3 streams with different amounts with different flow rates, but each stream will have the same concentration of the components, no? The same percentages of components present in each stream, which is also the same with that of the feed stream. So we could not really use that in our problem. So what we did is we used the mixer and reversed our problem, no? The feed became the output and the output streams became the input streams. Because in this case, the mixer really mixes the incoming streams, and so the feed composition also changes, no? When we change the composition of these streams, 'di ba? Like what we did kanina. So when we change this and this, the feed composition also changes. Okay, so um, we could report this, no? I think, how do we do that? Um, Maybe we could configure the page. A4. Okay. I think it's in the tools results. Okay. So click on results and click on create report, and available items. We just need to do the material streams, the feed, recovered and waste, and include the condi. I think we just need to include the molar compositions, no? We don't need the mixture properties. Molar compositions. I think that's it. So let's click on view report. Oh, wait. Wait. I think we have to click all. And is that it? Wait lang ah. Maybe we can do the mixers. No, it's just the material streams. And export data to file, maybe. No. Maybe print report. No, shucks. It's wrong. So, mixture properties. Why is there no report? Object type, property value. There seems to be an error. No. Well, let me just save this first and call this sample material balance computation. So I think there should be no problem with printing it. So let's click on results, create report, all the material streams, feed recovered, input conditions, molar. Okay, so let's just click this one. There. I think we do need to get the conditions, maybe. There. Okay, so for the feed, the conditions are this, the temperature, the pressure, the mass flow, and the molar flow, the volumetric flow, no? And okay, so this is the report of your simulation. I think we could change this, no? Change the title, change the comments. Maybe the title should be the activity title and the comment should be your name, I think. So how do we, let's play with that now. So let's check if it works now. Oh, it doesn't work. So how about clicking this and unclicking the other one? Oh, okay. So we need to at least click the conditions. So this is non-negotiable, and this one is what we wanted, no? The molar composition. Okay, so how about the name of this? How do we change that? Miscellaneous. Here. So when we click um, the settings, or we could click simulation settings, the miscellaneous here is the title. So maybe we could say material balance exercise, and the description is your name, for example. Okay, and so close this and click on create report, material streams, unclick the other one, include molar, view report. Okay, there you go. So this will now be your report. So whenever we have assignments or exercises, maybe I will ask you to submit this simulation report. Okay, so you could print this and maybe print it to PDF, no? And click OK, and maybe add it here. So material balance simulation result, and save. And then we have our PDF file now. Okay, my computer is working on it. Opening. And unable to open. So I don't know what's going on, but maybe we need to close the program first. No, maybe we need to close this first before. I think it's not yet finished. So anyway, you could figure this out on your own, no? Or let's try it. Um, oh, we already have it. Okay, now we're done. And okay, so I hope you guys learned. Um, I hope you guys learned something about this simulation program. No, so I think um, the lesson here is that we don't really get what we are looking for right away. No, you really need to explore. No, like I did explore the stream splitter and stream mixer, as well as this compound separator item here, but I did not get the answer using those, and ano, I was only able to answer the problem using the mixer. So you really have to uh, not give up on using this program in solving the a problem, because this program was created with a purpose in mind, so it might not be like really solving material balance problems, no. might not be for that, but still we could I think it depends on the user, no, how you could maximize the use of this program. So it still depends on who the user is and how patient are you in exploring the program, exploring its functionalities, no, and maybe thinking about your problem and how to translate an actual problem into a working simulation setup, a flow sheet setup. Okay, so